Okay, so in this section, we are going to take a look at a very important part of most, if not all, chemical reactions, and that is the idea of energy changes that accompany chemical reactions. So if you recall from our original definition or description of chemistry, we said that chemistry is the study of matter, the changes that matter undergoes, changes as well as the energy associated with those changes. So in the first few weeks of our class, we talked a lot about the study of matter, what matter actually is. In the recent sections, we looked at the changes that matter undergoes, which are your chemical changes or chemical reactions. And now we're going to take a look at the energy that is associated with those chemical changes and those chemical processes. So that's a big part of chemistry. And the study of that we'll define here in a little bit. That's commonly referred to as thermochemistry when we look at it in terms of heat changes. So before we get into some of the details, some definitions to start off with. Often we talk about energy changes relative to a system or energy changes relative to the surroundings. And then we also talk about the universe itself, not in terms of a like a physics setting where we talk about stars and galaxies and stuff like that. This is just in reference to what it is we are actually studying. So we can define the universe as everything, and that's the sum of, or it's equal to, the system, and the system is usually what is being studied, plus the surroundings. So this is everything else but the system. So obviously then, if we add together the system that we're studying plus everything around it, we end up with the universe, right? So those are important definitions to keep in mind, because when we start looking at changes down the road, we're going to define them relative to the system or relative to the surroundings. So for instance, if I have a chemical reaction that I'm performing in, let's say this is a test tube, okay, and I mix a couple of solutions in this test tube, this in here, that is my system. Right? That's where the chemical reaction is occurring. The test tube itself and everything around it, the air, the table that it's on, the test tube holder, the person holding the test tube holder, the room, the building, the city, the county, the state, everything else, that would be the surroundings. The test tube and everything else. And then sum, obviously, of the system and the surroundings equals the universe. So those are important terms to note because we will come back to them over and over again. When we study the transfer of thermal energy, which is often the most common form of energy that we are going to encounter in our level of chemistry, we refer to that as thermochemistry. And this whole section is about thermochemistry. You can think of thermo as kind of meaning heat. So thermochemistry is the chemistry of heat changes or the transfer of thermal energy. Okay, so we define heat then as this transfer of thermal energy. During a process, heat is either absorbed into the system or heat is released from the system to the surroundings. So we can look at heat changes. This again is relative to the system. Okay, so heat can be absorbed into the system heat can be released from the system during a process. Often when we look at so heat again is a transfer, is a form of energy. It's thermal energy, and then generally we saw earlier on there's an energy unit that we use in the SI system called a joule, uppercase J. There are other units of energy that are used that you would probably see more often. A very common one is called calories, and calories are abbreviated CAL, lowercase CAL. And that is equivalent to 4.184 joules. And the calorie, which is defined as the amount of heat required to raise 1 gram of water by 1 degree Celsius, so lowercase cal, is not the same as a nutritional calorie that you see on your nutrition labels, which actually has an uppercase. Okay, so CAL, big CAL, is not the same as lowercase CAL. This is a nutritional calorie. This is a regular calorie. We'll just say regular right now. And then the relationship here is 1 cal, big cal, is equal to 1,000 regular calories. And we can throw in some metric prefixes here. We can say 1 nutritional calorie is 1 kilo, small calories. Okay. So those are the most common units of heat energy that we'll see. The relationship between them here, calories, 1 lowercase cal is equal to 4, just over 4 joules. So when we talk about heat changes relative to the system, we can define a couple other terms that we're going to be using a lot from this point onwards. Okay, so if I have my test tube again, there is my system that I'm studying here inside of the test tube. If that system, let's say, releases heat, we call that an exothermic process. Okay, so heat is released to the surroundings. And if the system is a thing in the test tube, well, then the surroundings will actually be the test tube and everything else around it. So what you actually would detect here is that the test tube feels hot or warmer to the touch when heat is released. That's an exothermic process. The opposite of an exothermic is called an endothermic process. So we'll just use our same test tube here. If that process absorbs heat energy, okay, so now let's say the system absorbs heat. Okay, so it's now gaining heat energy. Where's that heat energy going to come from? It's going to come from the surroundings. So in other words, the surroundings are losing heat. So as a result, the surroundings will get colder or cooler. And the test tube being the immediate surroundings, that test tube will actually feel cooler to the touch. All right, so, a couple of things that may help you. So this is endothermic, by the way. So exo meaning to the outside, and then thermic meaning heat energy. So heat energy released to the outside, and endo meaning to the inside, and heat energy. You can, use a couple things here to help you remember what each of them actually means. So exo versus endothermic is relative to the system that we're studying in terms of the heat or the thermal energy changes. Now, thermochemistry is part and parcel of a much bigger umbrella called thermodynamics. And this is the study of the interconversion of not just heat energy, but other kinds of energy as well. And we're going to spend, if you stick around for Gen Chem 2, we spend a whole section on this. So we'll see again in 1515 if you take that course down the road. And we'll talk in a lot more detail about thermodynamics and all the different laws of thermodynamics. We do still need to define a couple different systems when we look at thermochemistry or thermodynamics. The first one is called an open system, and in an open system, that system can exchange both mass and energy with the surroundings. Okay, so if I have, for example, this round bottom flask that we have here. My reaction is happening inside. So there's my system on the inside. Obviously, this can release heat, it can absorb heat, so it can exchange energy with the surroundings. But then if this is left open to the atmosphere up here, and let's say we, boil this, for example, water can actually escape. So now it's exchanging mass with the surroundings as the water vapor leaves, or in some cases, the water vapor condenses, falls back in. This is called, we refer to this as an open system. So both mass and energy can be exchanged with the surroundings. A closed system, on the other hand, allows the transfer of energy, so heat energy typically, but it can be other forms of energy, but not mass. Okay, so here, in contrast to the one above, right, we still have our flask. Now it's actually, it's plugged or it's covered. Okay, so now the water vapor, if we were to make water vapor, it doesn't escape. It hits the bottom of the stopper. It comes right back into the solution. So this is a closed system, allows a transfer of heat. Heat's allowed to go back and forth, but not mass. And then the third type of system that we can define is known as an isolated system. And in an isolated system, what we're looking at here is a system that does not exchange neither mass nor energy with the surroundings. So yes, we still have our stopper that prevents the exchange of mass. But now what we'll see here with our flask is that it is actually now insulated, right? It's surrounded by some sort of an insulating jacket, probably styrofoam or something else. It's a good insulator. So there is no heat energy that can escape. No heat energy can be absorbed. This is known as an isolated system. And we will actually do some experiments in the laboratory that involve one or maybe two of these different types of systems.